Thanks everyone for showing up for the session that starts at 5 when I know there's also beers outside. So, welcome. I hope you guys are going to enjoy yourself. This session is titled A Day in the Life of a VSAN IO. My name is Duncan Epping. I'm a chief technologist working for the Storage and Availability Business Unit, primarily responsible for virtual SAN, virtual volumes, and the vSphere APIs for IO filtering. I'm here with my good friend, John. John?
Howdy.
You don't want to introduce yourself?
I'll introduce myself. Here we go. My name is John Nicholson. I'm a Senior Technical Marketing Manager in the Storage and Availability Business Unit. I'm focused on the core vSAN product and functionality. I was going to say I've been with VMware a year now and excited to be here.
Great. So let's get started. Short disclaimer, I'm not going to go over it. I'm sure you guys have seen thousands of these so far, so let's get into it straight away. The agenda is pretty straightforward. I'm going to do most of the talking at the start, so I'm going to do a bit of an introduction about vSAN. We'll do some polling around, who has seen vSAN or not in a second. Then I'm going to do a bit of a deeper dive, what is vSAN actually about, what does it look like. And then, some of the failure scenarios and the IO deep dive is what John is going to do. So I brought him in. He's the proper geek in our team. He knows it, vSAN inside out. So he's going to handle the challenging stuff. So let's get started. Most of you guys have probably seen this picture by now, right? The software-defined data center is something that VMware has presented for years. And hopefully, or probably, as most of you guys know, we've solved the compute challenges that most people had in the data center over the last 10 to 15 years. There's two challenges in most data centers as it stands today that we haven't been able to solve, but we are capable of solving as it stands. Now, first one, networking. Are there any networking administrators in the room? Just a couple. We can take them, so we can blame everything on the network from now on. Now, the other big issue, of course, that we have is storage. And with vSAN, we're aiming to solve that problem. There's a couple of ways we go about solving that. Now, before we get into that I actually want to emphasize something that I think is really important. When people start talking about a software-defined storage solution or a hyper-converged, but primarily about a software-defined storage solution, they tend to talk a lot about the software aspect. What a lot of people tend to forget is that the hardware aspect is still really important, right? You can't run any software without those particular hardware components that it requires. On top of that, for instance, when it comes to vSAN, it's critical that you use the right hardware as well, right? So you can't expect 50,000 IOPS from an 80 IOPS drive. It doesn't work like that, even not with vSAN. It can do a lot of cool things, but it's not capable of producing magic numbers. Now, as it stands in the world today, you see a lot of shifts. You see a shift going on from an infrastructure perspective. You see a lot of new storage solutions. Companies like Tintree, Nimble, Pure Storage, you name it. Now, all of them exist today, in my opinion, because of the big shift that we've seen from a hardware point of view. So the introduction of flash, SSDs, right? But also the introduction of 10 gig networks, InfiniBand, RDMA, you name it. All of those changes, as it stands from a hardware perspective, actually allows us to start making a lot of changes from an infrastructure point of view as well. And that's what we're going to talk about in the upcoming 50 minutes. Now, if you look at vSAN, we have one goal, and that's make your life easy. I bet most of you guys, and women as well, let that be clear, most of you want to be this person, the lazy admin. I think the lazy admin is the best admin. As my friend Ellen Renouf would say, an admin should automate everything end-to-end and not care about what happens on the back end. It should all happen automatically. Now, that is what vSAN does for you as well. It does the automation for you, not through using something like PowerCLI or Perl or you name it, but it's actually baked into the product. So a lot of the things that would normally be a manual task from a storage perspective are now being taken care of by virtual SAN itself. So that's a proper form of automation. And that's our key aim, to make you a lazy admin, preferably, sit like that, and maybe even on the beach, who knows. Now, if you look at the operational aspect of storage in the traditional world, most of you guys have probably seen pictures like these, right? So you're talking to one of your app owners and he wants to deploy a database, and now you need to start thinking about what kind of rate levels you want to use, what those disk groups need to look like, how many IOPS they require. Does something like, for instance, replication need to be enabled? Does steering need to be enabled? All of the different things you need to think about. Now, that is one of the things that from a vSAN perspective, we're aiming to take away. A lot of these concepts no longer exist within vSAN. You don't need to really think about a lot of these aspects anymore. It's all baked into the product. And if you do want to make changes, we will allow you to make certain changes, but we'll get into that in a second. Now, the key reason, or the key question that typically then comes is, okay, how are you guys capable of doing this? How did you guys introduce these changes into your stack? Well, there's one layer here that's really important, and that's vSphere, right? So we're talking about vSAN today, but the key reason we are capable of doing vSAN is because of the hypervisor. We own the hypervisor, right? And when it comes to it, all of the IOs will need to flow through the hypervisor. And as soon as it hits the hypervisor, we can start doing smart things with it. Today we're talking about vSAN, but the same applies to virtual volumes or the vSphere APIs for IO filtering, for instance. Now, when it comes to vSAN, this is one slide that, a lot of my colleagues will probably not even discuss, but I think this is the most important slide of the deck today. There's a lot of crazy stuff that John's going to talk about, but this is key, policy-based management. Why? Well, as an administrator, all of the stuff that you will see along the session when it comes to the IO flows, and you name it, all of that is influenced and impacted by the way you've specified your policy. So when it comes to VM management, the key thing here is that instead of, placing a virtual machine on a particular LUN or a particular data store, a particular type of VMC or NetApp storage, within vSphere right now, with vSAN, the only thing you need to do is you create policies. Within those policies, you define what the characteristics of your workloads are. So do you need to have a particular RAID set configuration? All of those different types of things. Do you need to have a certain amount of cache for a particular virtual machine? You name it. You specify that in policy. You attach the policy to a VM, and then the VM will get deployed in a specific way on the virtual SAN data store. And that is truly key when it comes to virtual SAN. So, remember this slide. Now let's get into vSAN itself. How many people of you have actually used vSAN already? Show of hands. That's actually a lot of people. I didn't expect that, because last year we did a similar session, and we had about 20 people raising their hands, so it's good to see the adoption going up. It also means that I can probably go, spend a bit less time on the introduction slides, which is good. So what is it? Well, apparently most of you guys know what it is because you've been using it for a while. But, in short, it's a hyper-converged infrastructure solution. Some people refer to it as software-defined storage. Why? Well, it comes with vSphere. It's a software solution, and VMware doesn't sell any hardware. So software-defined storage. On top of that, you can refer to it as a distributed scale-out storage solution. Key thing with vSAN is that it's fully integrated with the vSphere, with the vSphere stack. So if you understand vSphere, you understand vSAN as well, right? Those who haven't used vSAN yet, if you know how an HA DRS cluster works, if you know how to enable HA, which is literally 2 clicks, then you know how to enable vSAN as well. It's about 2 or 3 clicks, maybe, maybe 4 with the latest release, but it's really, really simple. Now, if you look at the vSAN stack itself and what it looks like, it all starts with vSphere and a bunch of x86 hosts. That's what it starts with. Now, the next thing you will need to introduce is some form of capacity or performance, right? So you have a bunch of SSDs, one of them being used for caching, the other ones being used for capacity, or you have one SSD and you have spindles as well, depending on what you prefer. And what vSphere actually grabs all of those disks and it shares those out as a common data store to the cluster itself. So within the cluster itself, you'll end up with one data store, only one. You can only have one vSAN data store within a cluster. Now, instead of creating multiple data stores, as I just said, we have those policies. And as soon as you set this up, you create those policies and you assign policies to virtual machines, and those virtual machines will end up on that single data store. That's the basics of virtual SAN itself. Now, if you look at the customer base, Pat Gelsinger said it on stage today, we have about 5,000 customers, or over 5,000 customers using vSAN as it stands today. Majority of those customers actually are larger customers. I had a whole bunch of questions today with regards to those numbers, and a lot of people assume that they're mostly smaller customers doing 3-node clusters or 4-node clusters. Truth is that they're mainly enterprise customers. We do have a lot of SMB customers, but we have a lot of enterprise customers actually using this in production environments for their DMZ, or maybe, for a management cluster as well. There are different type of options. There's a couple of cool use cases that we've seen when it comes to vSAN over the last a couple of years. The Oil platform is probably one of my favorite ones. It's a customer from the Nordics who deployed vSAN on a couple of oil platforms, and they're actually managing those remotely over a satellite link. Because these oil platforms are out somewhere in the sea, they're managing them remotely over a satellite link through a centralized vCenter server, which is, pretty unique and I think a cool solution as well. We have some other customers doing crazy things with vSAN, like vSAN on a submarine, for instance, which I think is a pretty cool solution. Now, of course, besides these weird scenarios, there's a whole bunch of different use cases for virtual SAN. A lot of people ask, what should I be using it for? Well, basically, if you look at the list, you can use it for anything. We have customers using it for Oracle, for Exchange, for SQL, but we also have customers doing it for test dev environments. I was just talking to a large American airline, and they were mentioning to me that they have a really big environment where they basically run all of their test and dev workloads on top of vSAN. And if a new release of their software comes out, they just spin up new virtual machines on top of vSAN, and that's how they go about doing it. There's two interesting use cases. I've already mentioned one of them, the management cluster, but the other one is the DMZ. How many people are storage administrators in the room? Okay, quite a lot. That's good. So the funny thing is when you start talking about vSAN, a lot of the storage people feel threatened because, it's not an EMC product, it's not a NetApp product, it's kind of different than what they're used to. And the way I tend at least to convince them with the first use case is when you start talking about some of the use cases that are challenging. DMZ is one of those. Why? Well, in most DMZs, they don't have a dedicated storage system. They need to have an isolated SAN segment for a DMZ, but they typically end up using the same storage systems. Now, that imposes a risk because you can imagine when there's 5,000 or 10,000 or maybe, a million people trying to hack into your website, then not only it overloads the website, but it potentially overloads the storage system as well. If you have a fully isolated vSAN cluster for that purpose, it will never impact your production environment. And whether that's vSAN or another storage platform is besides the point. So you have a fully isolated environment. And the same applies to management, right? A lot of customers have a management cluster, but if you're running your workloads, which are managing your storage system, for instance, right, on the data store, that's actually sitting on that exact storage system that you're managing, that you can imagine you have a circular dependency. If that storage system fails, then now your management tools are gone. Right? So that's a great way of introducing vSAN into your environment. There's a whole bunch of other use cases, but we won't go into depth. Now, there are multiple ways of deploying vSAN. Actually, two of them. First of all, hybrid. So majority of our customers, as it stands today, do hybrid deployments. So they typically use one or two SSDs, depending on how many disk groups they have, and then they will have an X amount of spindles. Truth is, if you look at the world today, most of our customers are moving towards all flash. The key reason for that being is the price of flash is going down rapidly, depending on where you are in the world, by the way. What a lot of my American colleagues don't realize is that the prices in Europe are slightly different than the prices in the US, unfortunately. And as some of my friends know in South Africa, it's even worse. So depending on where you are, that may or may not be the case. But the reality is this is going to change fast. If you look at the price of flash today, 50 cents per gig is more or less what some of our friends are hitting, our partners are hitting as it stands today. So that makes it really attractive to start looking at these types of solutions. Now, we'd like to put these numbers up here. It says 100K IOPS per host. We actually managed to hit 150,000 IOPS per host. Last week, I believe.
Yeah, the Intel booth, they've got that demo.
Exactly. So they have an Intel demo that shows 150,000 IOPS per host. But that number is kind of irrelevant. Now, let me ask this question. How many people have received a phone call from one of the app owners saying, I didn't receive my 1,000 IOPS you promised? Hey, there's one guy. Okay, I'd like to talk to you later on. How many people have received a phone call from an app owner saying, my application is really slow. I think there's something wrong. Must be a lot of latency. Majority of you guys, right? And that's the important thing here. It's a sub-millisecond latency when it comes to all flash. That's the key thing, sub-millisecond latency. And this is just, where we are getting started. You can imagine with things like NVMe, NVDIMM in the future, it's going to go down even further. Now, before we start getting into the more deep dive stuff, first of all, this thing, because I think it's important to realize. We just spoke about all flash, and we spoke about hybrid. vSAN has a caching mechanism. There's always one device responsible for caching, and depending on whether you're using hybrid or all flash, it is going to be used in a different way. For hybrid, the way it works is 70% of your capacity is going to be used as a read cache, 30% is going to be used as a write buffer. Now, when it comes to all flash, that whole device is going to be used as a write buffer itself. So the full capacity of that device is going to be used as a write buffer. Now, some of you may have read some of the articles that I've written about the caching device, and I've mentioned at some point that the limitation of the caching, the caching partition is 600 gig. And a lot of people say, you know, what if I have an 800 gig SSD? Do I lose 200 gigs? Well, that's not how an SSD works. The way an SSD works, it will actually use the additional capacity for instance, if one of the cells is unrepairable, it will actually move the data to the additional capacity that's available. And also, it will just keep going through the cells itself. The partition itself is just a logical partition. It doesn't necessarily represent the physical blocks. So that's important to realize. So you can use any size you want, and you should be using any size you want and any size that comes out of our calculators as well. Now let's take a look at VSAN in a bit more deeper fashion. First and foremost, VSAN is an object-based storage platform. So why is this important to realize? Well, if you look at a VMFS data store today, all of the VMDKs and name it on that are actually files. Now, if you look at VSAN, they are being treated as an object, which is slightly different. Now we'll show you what the difference is in a second. But keep this in mind, it's an object-based storage platform. The other thing to not forget is that VSAN was designed as a generic object-based storage platform. It wasn't designed as a virtual machine object-based storage platform. I will explain in a second why that's important. Now, before we can actually show what those components result into, every single time you create a policy, that policy determines what your components will look like on the VSAN data store itself. So you design and create a policy first, and then the outcome will probably look something like this. So if you look at the diagram itself, you see a VMDK, which is the virtual disk at the top. In this case, you see a RAID 1, right? And the object is the VMDK itself. Now that object is split into multiple, as we call it, components. RAID 1 ensures that you have multiple copies of your data available across multiple hosts. In this case, because we specified RAID 1, with one failure to tolerate, we have 2 copies of the data. We've also specified some form of striping, which can also be done through the policy, which means that you will have multiple components within a host or potentially across hosts as well. So VSAN takes care of that logic. So if you specify I want to have 6 stripes, then VSAN will place those objects somewhere in the cluster. You don't need to worry about that. We will make sure that we place them in a logical fashion. But this is the key thing, right? So if you look at that layout, that's all specified through policy. It's not something you need to worry about, but it's something that you can see in the UI, and something that every once in a while you may wonder why that happened. Now, the first one I've already mentioned, I said RAID 1. This is where you specify the availability, which is numbers of failures to tolerate. So depending on how many you've specified, you will have 1 or multiple copies of your data. Hopefully more than 1, because we're talking about availability here. If a host fails, you still want to have your data being available. In this example, what you see is you have a virtual machine with a disk, and that disk is getting placed on 2 nodes, and there's a witness component as well. You can imagine that if there's a partition, for instance, from a networking perspective between those hosts, that we want to make sure that we know who owns the data. So that's where the witness comes into play. The other thing that's key here is that if you look at ESXi02 and ESXi03, which are both carrying the VMDK, is that both of them are doing I/O as well. So we're talking about read I/O. So 50% of the read I/Os will come from one host, 50% of the read I/Os will come from the other host. But John's probably going to go in a bit more depth when it comes to that. I've already mentioned the striping, and with striping you can ensure that data is laid out across many disks. In an all-flash world, this is something that you typically probably will not end up using. In a hybrid world, this can be very useful, depending on how fast your spindles are. You can imagine that if you have a spindle doing 80 IOPS, and your VMDK, the whole VMDK component is stored on that single 80 IOPS disk, then that's the limitation you may have from a performance perspective, depending on how much data is cached. So that's where striping can come in handy. The other thing that's important to know and important to realize is the fault domain concept. I don't know if people have already played with the fault domain concept, but I think this is something that's really cool when it comes to vSAN. So if, for instance, you have within your data center multiple racks and you want to ensure that you can actually tolerate a rack failure, what you can do within the UI is just say, okay, these two nodes are part of rack 1, these two nodes are part of rack 2 and 3 and 4, and if anything happens to that environment, I will always have copies of my data available in those different fault domains, which I think is a cool solution. Now, I'll do a couple of slides of the failures, hand it over on the last slide, because I think you thought that was a really exciting slide. So let's talk about some of the different failure scenarios. Before I get into it, does everyone understand what vSphere HA is and what it's for? Anyone who doesn't understand? No one? Great, okay. So let's get going. Now, if you look at this example, in this case, we have a single ESXi host which is isolated from a networking perspective. Now, what vSAN simply does, it has a coordination mechanism with HA, and basically what ends up happening is that those three nodes realize that the first node has disappeared. So the basic thing to do is restart that virtual machine, and we can simply do that because that virtual machine itself has lost access from a storage point of view to the components itself. So vSphere HA doesn't even need to detect anything. If those components are still being used, it can just restart those virtual machines as the lock on that particular virtual disk has been lost. So the virtual machine will be restarted in about 25 to 30 seconds, something like that. That includes the vSAN failover. So there's no particular mechanism for vSAN when it comes to doing that failover itself. It's HA actually taking that action. It knows that the host is gone. It will restart the virtual machine fairly quickly. Now, depending, of course, on how you specify and set up HA from a host isolation response, that virtual machine will either maintain running or be killed. In the case of vSAN, always ensure that when you set up HA, that you have it configured from an isolation response perspective to kill the virtual machine. So power off. Don't select shutdown, because shutdown will actually try to go through the virtual machine itself and through the guest tools to power off that virtual machine. But guess what? It has lost storage, so it's not capable of doing anything from a VMware tools perspective anymore. So make sure you set it to power off. At that point, the virtual machine will be killed, and even if it comes back, there is no risk associated with it. Now, the other thing that potentially could happen is, hold on. The other thing that potentially could happen is that you have multiple hosts that are being partitioned from a vSAN point of view. Apparently, something went wrong with the diagram. There's a line missing. This should have been the diagram. Now, in this case, you actually have two hosts that are being partitioned from the cluster itself, or four hosts actually. So if you use ESXi01, ESXi02, 7 and 8, and 7 and 8 are actually carrying the witness itself, so the witness component. Well, in this case, what will happen is although the hosts ESXi01 and ESXi2 can still ping each other, vSAN will realize that something has gone wrong. The witness is not accessible anymore within the cluster itself. HA will notice that that virtual machine that appeared to have been running all of a sudden doesn't appear to be running anymore. Although it's still running on either ESXi02 or ESXi01, 3 to 6 don't know that it exists anymore because it's not capable of actually communicating with 1 and 2. So what will happen in this case is that one of the hosts in that particular partition segment will actually restart the virtual machine itself, or will gain access to that particular object. So whatever happens from an HA perspective, vSAN is always capable of restarting that particular virtual machine. Let me hand it over to John, who's going to handle the last partition scenario.
So this is a more interesting partition scenario, because classically when you have a clustered system and you have 4 nodes within SQL, you always want an odd number for quorum reasons. from a host perspective, if you had SQL servers or things like that, or you had to have some type of external witness system to manage quorum. In this case, we have 4 hosts, and we're partitioning them 2 and 2. And the key thing to note here is that the quorum, or how we identify which copy of data should be active to prevent what's known as a split brain, where both copies go active, which would be the worst of all cases, and you can't do with vSAN, no matter how hard you try. The key thing to note here is that the quorum is being managed by the object system. So in this case, we can see that we've got 2 of the 3 components on one side. And one thing to note, if we had other virtual machines in this cluster, that they had the majority of their quorum on the left side instead, that you would actually have HA firing off simultaneously. And you would have some VMs go to the left, some VMs go to the right, but never virtual machines starting on both sides. We properly fence that and manage that. So this is one of the cool things about the visibility and the integration between vSAN and HA, and that it's able to intelligently understand what's going on all the way back to the component layer.
Yeah, before you continue, I think one thing to point out here is that when you have this partition scenario, that virtual machine that's running in the first partition actually remains running as it stands today. The key reason for that being is that from an HA perspective, it's not an isolation, it's a partition. So it's still things that it can still access all of those components from an HA point of view. Now, what we've done in the latest release to actually mitigate this scenario is that within vSAN itself, we introduced a mechanism that actually detects this particular scenario and will notice that that virtual machine that's running actually has lost access to all of the different components that are available, and it will actually kill that virtual machine in particular. So the key reason we introduced this was for a stretched clustering environment where you can end up with a situation where half of your data center literally has disappeared. So that's why we introduced that mechanism.
The natural predator of uptime in a stretched cluster, of course, the backhoe can strike and separate that environment. So while this may seem unlikely that you would have half and half, particularly in a stretched environment, this is a real threat. So let's get a little deeper into the I/O structure and what's going on within vSAN. So write acknowledgement. So when a write comes in from a virtual machine, in this case we've got RAID 1, we want to make sure that data is protected. And a common misconception I get a lot when talking to people is they assume one copy is always local. That's not true. It's going to take the same amount of round-trip time to go to one local host as 2. So we don't just move data arbitrarily around, because that starts incurring performance penalties, and things like DRS actually become ugly because they cause secondary performance costs if you have the equivalent of a storage vMotion happening behind every vMotion. So in this case, the virtual machines here, so the writes are going to go through the system, and they're actually going to go to both hosts simultaneously. And we do not acknowledge that to the higher layer within the environment until we've received both of them. Now on reads, things get a little more interesting. So the guest OS will issue that read command initially down to the HBA layer, and this will go in, and we're going to basically look at the reads across both sides. So every other block, our 1 megabyte block size, it's going to be split to where, evens will go this way, odds will go this way. There's a reason for this, because we have cache, particularly in a hybrid environment. We don't want to have duplicate copies in cache ever. That's a waste of read cache. Now, write cache, obviously, things like that have to be mirrored. But reads, we want to try to get twice as much cache instead of mirroring. So this way, that data, as it gets pulled up into the read cache, will go through. So as those blocks come up, to go even more granular, going a step even lower. So let's say you get a 4 kilobyte block request. So first, we're going to check that read cache, that SSD in the hybrid environment. We're going to look for that block. If that block's there, we serve it. If it's not, we got to go all the way back to the capacity layer. This is called a cache miss. If you get a lot of these, you can start to potentially overwhelm the back end. We can do striping and other things to mitigate. So one really cool technique we do to cheat and accelerate when you start getting misses, they tend to be grouped together. And so what we'll do is, with that first 4K miss comes in, we'll request that block. We're also going to request every other block around it, within that 4K request, we're going to request everything around it within that 1 megabyte block. We're going to rip it all up into memory and promote it up into the cache together. So that way, if you get one cache miss and someone asks for the next couple blocks around it, it's actually been gone not just to the cache, but also all the way to actual memory, host memory within local to the host. Now with all flash is a bit different. As we discussed, in an all flash environment, we have 100% of that initial buffer drive is acting as a write cache. And acts for two reasons. One, endurance. Those are higher rated endurance drives. Although endurance is often an overstated. The real important reason of why we have two different classes of flash, of your higher endurance, higher cost, and your lower endurance capacity, is those lower endurance capacity drives, besides endurance, they also have another flaw often. They don't have as consistent of write latency. And we want to serve highly consistent latency on reads and writes. And so in this case, we will first check the write buffer because there may be data that was waiting to be destaged down lower. So we're going to check that. We're going to check that from the read. We'll look there. We'll also look in the client cache. It may have been in that amount of memory. And then we'll go down lower and again, go down to the capacity tier, check there. We'll return that data to owner. And again, we're striping reads across both sides. So I mentioned client cache. So we have, starting at 6.2, previously there was actually, people would ask, are you using memory for caching? And the answer, we would often say no, but it was actually kind of a maybe. So there were these tiny little caches, there were these one little megabyte read ahead that I mentioned previously that did exist, but they were very small. There's only one per component. So moving forward, we now have a unified cache in each host called client cache for this purpose. And this is 0.4% up to 1 gigabyte. And in most cases, you're going to have 1 gigabyte on a host. And this is actually local. So as I mentioned earlier, we don't try to have data follow VMs around. This is a case where it will. The reason why is because memory is very low latency. Modern 10 gig networks can hit 350 nanoseconds. They can be very low, and there's new advances coming with RDMA and so forth. But memory is even lower than that. It's incredibly fast. So we didn't want to waste memory and put it behind a network. And so this will act as a local read cache. Again, 1 gigabyte per host. Our performance team within product enablement did some testing. There's a white paper. I encourage you to read a reference architecture. VSAN 6.2 and Horizon 7. They saw 75% fewer reads, 25% latency. Now, the only downside of these awesome caching technologies is they don't make your performance graph spike a lot on the back end, and it looks less impressive. You don't get to brag about as many IOPS, but the best IOP are the ones that you don't actually go to disk for in that case.
And that's actually a good story. I was talking to a customer the other week. They actually just implemented 6.2. And because of some of the changes that we've seen here, they've been capable of driving a lot more IOPS at a lot lower latency. So what they did recently is they actually moved some of the databases that they had over to this new vSAN platform without telling the database team. Because, the database team was always being difficult about storage and some of the particular requirements that they had. So what happened is that the database team started to run this particular query that they run once a month, which used to take about, 12 to 13 hours. Now, all of a sudden, they had a result back within an hour. So they figured, something went wrong with that particular query. So they spent, I think, about 5 to 6 hours debugging what went wrong with the environment itself. Actually, nothing went wrong. Someone moved that particular database over to vSAN. I think that, it's probably the best story you can get from a customer. It's a bit of a shame that these guys wasted 5 to 6 hours, but, it's a great story for me up on stage at VMworld.
Yeah, there we go. I will note, for those of you who have noted, that VMware has another RAM-based caching solution known as client-based read cache. The product name for that, when used within View, is known as View Storage Accelerator. This does coexist with that. It can complement that. Client-based read cache does some other things. It does some deduplication within that, and it's used commonly for replicas within link clones environments. So it can also be used in full clones. But there are limitations, like certain things like writable app volumes, other things within VDI, the management stack. And also, you have to wait on it to build a digest, so it can actually slow down a recompose process. This is an immediate cache that's available, and this is also flexible. This works with servers and other workloads. So checksums were a feature we introduced in 6.2. And oftentimes people just looked at this as a checkbox, but I did want to expose some cool things we're doing. We wanted to make sure, as a general mantra for data protection, that this was generated as early as possible and verified as late as possible in the environment. So in this case, the write comes in to the host, and the local host immediately generates that checksum. We use CRC32. The reason why, it's very strong, very reliable. And second, modern processors are really good at it. The amount of CPU overhead is completely negligible from a checksum perspective. And in fact, CRC32 offload has been around since Xeon 5500, circa 2008, I think. It's been so even if you got some older hosts, they should be able to beat that up pretty quickly. So you've got your transport over a network. And in this example, there's one local copy and there's one remote copy. Now, right before that data is written to disk, it's verified to make sure that at no point on this in-flight operation across the network that data was corrupted. So this host is going to, the host on the far right side here, host 3, is going to make sure that that data was not corrupted in flight. Now, when you read that local host, it's going to pull up both the copy of the data and the checksum. And we're going to see, and they're going to be verified again at the last possible moment. As that data comes over, the last host, it's going to verify that. And if that checksum does not match, we're going to go repair it. So in this case, it's a mirror. If this was a RAID 5 or RAID 6, we do an erasure code, repair, and do that. Now, this is all well and good. So every read, every write is checksummed, every read is verified. But what about the data, the other data out there, that data that sits there cold, that everyone's ignoring all the time? So once a year, if a block has never been read, we will go scrub it. Now, this is adjustable. You could change it to, once a quarter, stuff like that. But this, combined with the high bit error rate, or not high bit error, but the low chance of bit error rate, 10 to the 15th or so of enterprise-based flash devices, does a good job of fighting off, silent data corruption and what's often known as bit rot within the industry. See if we can move forward here. So, new feature within 6.2 is deduplication and compression. We're very excited about this, and this combined, again, with some of the other things like RAID 5 and RAID 6 and the 50-cent flash we can get from major server vendors, allows all flash vSAN to have incredible value and proposition. So some things we do with this, which are really cool, is one, we chose a very granular, best-in-industry class, 4 kilobyte block size. And what this means is when you're trying to find duplicate data, the larger you're scanning, the less likely you're going to find an exact match for that. So the smaller this is, the more likely you're going to find deduplication. When you go up to an 8 or a 16 kilobyte or a larger block size, the only thing you're ever going to find are maybe the operating system files or some basic stuff. It's going to be a pretty low chance of finding overlap. The other thing we also do is we use LZ4 compression after we do that deduplication, which is very powerful. So one thing I want to talk quickly about is the file system layout. It changes. When you turn on deduplication, our deduplication boundary is a disk group. And so what this means is all data going into a disk group is compared against itself. There's twofold reasons. One, with a global deduplication scheme, any corruption of the hash table can corrupt globally. So we want to avoid any risk of that and keep this manageable. The second is when you do a global deduplication system, you have to run something like an in-memory database, which puts an immense amount of resources. And if you've used vSAN, which a lot of you have, you know the CPU and memory overhead is very negligible, and we want to maintain that. So what we do is as that data comes into the disk group, in this case we have 2 VMBKs with a lot of data that overlaps. The first one, previously when hybrid, you knew exactly which disk you were going to. But since you can't control where a match happens, we basically stripe by default across the disk groups within all flash. And that does give some performance benefits. It manages endurance a bit, as well as just the functionality of how deduplication works. If we had each VMDK hard going to a VM and made our deduplication boundary much smaller, it would be much less likely to find duplicate data. So we didn't want to take that trade-off. So some other things about the I/O path. This is a very interesting implementation. There's 2 classic ways to implement deduplication. You have what's known as inline, where every single write coming in is scanned immediately. This often requires dedicated CPUs. This requires, large amounts of memory. There's a lot of overhead associated with this. The other option is known as post-process, where the data is written. In fact, if you've ever used a VTL or a backup target, a lot of them do this. The data is written, and then later something comes along, reads the data back into memory, scans it, writes it back. The problem with post-process is, besides all those extra I/O hops and CPU for that process, it's nice because you could schedule it at night maybe. But the problem was it starts fighting your backup windows and other problems. The other thing is also with post-process is it creates holes in your file layout. So now you have to run a defrag process. So in addition to all this extra write, read back, punch hole through, update metadata structure, now you're shuffling data around. This leads to inconsistent performance. And we want to deliver consistent sub-millisecond latency. I've had some very large institutions run some very long torture tests on vSAN, and what they noted against some competing systems was that we're able to maintain very consistent latency for hours, and days, where other systems will start introducing variability because of how the data reduction is done. So looking specifically at the deduplication process, we use SHA-1 for our hash mapping. SHA-1 is, again, very fast. Our friends in the CPU industry, like CRC32, have found ways to accelerate this. Note, this is not used for security. So while SHA-1, there are cases, to create an artificial case for security cases, your chance of a collision are insanely low. It's in the hundreds of exabytes or something exotic. So the dedupe table is very strong. The hash map is not fully stored in memory. The reason why this is when you go to a 4K block and we store that in memory, the amount of memory you'd have devoted per host, you'd have 80 gigabytes or 100 gigabytes in some cases. You start having these large amounts of memory. We don't want to waste memory. So the hash map is stored on disk. But we do have a reasonably sized, small memory cache that's used for common hash blocks to prevent you from always having to do a double dip, always having to look up the block, then go read the block. So as we go through, one thing I want to note is first, when the write comes in, we acknowledge it by the cache. So we're not actually doing the dedupe up front. And a lot of writes have the lifespan of a NAT. That write comes in, it's immediately overridden. So why waste CPU on processes like deduplication and compression if the data is about to be overridden anyways? So we don't do that. So the cache data is fully hydrated. Now, as the data is pushed out of that write buffer and moves down and goes cold, that's where the scan happens. And the first thing that happens is we look for that SHA-1, and that's an inline process there, but it's an inline after the initial write buffer. So that's how we cheat to a degree and keep CPU overhead and memory red and things like that minimal, while still not having to go to that post-process that I described that carries a lot of overheads. Now, after we look for duplicate data, we then compress. And the reason why we do it after is there's no point in compressing data that we already have a copy of and we already know what it looks like. We're going to use LZ4, which I said before is very fast. And we're also going to avoid compressing duplicate data. So if that data does not compress well, we're going to write it fully hydrated. So if it was a 4K block and only compressed to 3.5, we're just going to write it fully hydrated because we don't want to waste CPU rehydrating compressed data that never compressed well to begin with. Now, we can still get very good compression because of LZ4. We still get very good dedupe because of 4K block. But these little tricks allow us to have an inline type process without the trade-offs while still keeping the CPU and memory overhead typically to no more than 5% in addition to what you're currently doing. So within RAID 5 and RAID 6, which also came out, these are also all flash technologies. Now, what I will say here is this does happen because of how the data is persistently written. This happens in the write buffer, so that those 4 copies will go through all 4 disk groups in this 4-host environment. And that data is written. And note, anytime you have a RAID 5 or RAID 6, like you've worked with previous, XOR type logic, you have to read the data in the parity copy and then write that. So there's a little bit of an added latency hop in that you have 2 separate, operations versus 1 before. That said, with low latency networks, incredibly low latency flash, in a lot of cases, this overhead is acceptable. And one thing also I want to put out as well, deduplication and compression, great low overhead feature you turn on, just checkbox turn on for the cluster. This is one that you can actually turn on a per component basis. So if you have a database where maybe the actual data itself is largely read heavy, there's not a lot of writes, performance is fine, you could turn on RAID 5. Maybe you have a log volume that's write heavy, on the same virtual machine you could assign that. And you could even change them on the fly. It's the nature of how the object system works. Now with RAID 5, we use a 3+1 layout. Now this is currently fixed at 3+1. That said, Christos has mused that if enough customers come up with some other use case or demand, please bring that forward. But keep in mind here, this is a great blend of capacity and performance in terms of trade-off. So with a 3+1, previously a 20 gigabyte VMDK would have consumed 40 gigabytes. Now it only consumes 27. And as we expand out with RAID 6, that 20 gigabyte, instead of consuming 60, or prior to this, for a fault tolerance of 2, we would have had to have 3 copies of data. We now only need 30 gigabytes. So this makes FGT2, if you've got a cluster that's large enough, 4+2, you've got that 6-host cluster or more, that makes FGT2 almost a default standard for a lot of volumes that aren't really the crazy heavy writes, I would say. I think you've got an excellent blog post to this effect.
Yeah, I actually think that that's what a lot of customers are doing as it stands today. If you look at the RAID 1 configurations in hybrid, and then if you look at the RAID 6 configuration for all flash, the cost of all flash RAID 6 is actually cheaper than the RAID 1 for hybrid. So, it makes sense to actually do RAID 6 when it comes to that, because you're capable of tolerating more failures. The other thing that I wanted to mention briefly is when it comes to erasure coding, there's a whole white paper on the topic, or Christos has wrote an excellent blog post on it. If you're interested on how the details actually work, go to virtual blocks. It actually explains all of the details around erasure coding. One thing that I think is important to mention is when we do the erasure coding of particular blocks, right? We have a 1 meg block size, but if a write comes in that is only 4K, for instance, we don't need to make a modification to that full 1 meg block itself. So we make a modification on a 1K or a 4K level. We make changes for that parity as well, which is also particularly small, and we actually distribute that again over the network. So we avoid that 1 meg overhead by chunking it up in smaller slices as well. I think that's important to know when it comes to erasure coding.
Yep. Yeah, that blog post is awesome. There's some great links to, I think, Planck's theorem, some other stuff. If you want to go on a really nerdy math deep dive, go find that on Virtual Blocks is our storage blog. One thing I wanted to note is swap placement. So swap, which is what you use as a reservation of memory, in case you get into overcommitment, you start having to, and all the other functionality, transparent page sharing, everything else, compression, has failed, and you start, ballooning, and you actually start writing memory to disk. By default with vSAN, the space is hard reserved because of how it works under the policy engine. That said, you can disable this. Here's the script for this, and actually if you go to Jace McCarty's GitHub there's a nice script that'll blast this across a cluster. So if you were not planning on overcommitting memory, and let's say you have 200 gigabytes of RAM per host that you're allocating, this is a free way to get 200 gigabytes of storage back per host.
Yeah, and a funny thing, this feature was actually designed because a customer we had a discussion with a customer. They said, well, we have a large environment, about 2,000 hosts, 3,000 hosts. We have many virtual machines, and the cost of swap for vSAN is actually quite significant. So we had a discussion with the engineering team. 3 months later, they actually introduced this feature in the product. So I was quite surprised about how agile they were. It also says something about how receptive the engineering team is for feedback. So if any of you are actually doing one of the Meet the Expert sessions with the engineers or with the product managers, or you're doing one of the group discussions, and you have feedback from a feature standpoint or something, you want to see introduced in vSAN, please speak up. You can also come to us at the end of the session. We're, of course, more than happy to help you guys get new features into the product itself.
Yeah, no, that's really awesome. Particularly as we started seeing this trend and shift to all flash, people really didn't want to be holding that space back. One other thing I wanted to note is the snapshot layout, and there's some great papers that Cormac Hogan has put out on this and some blogs. So, and also this is a shameless plug for my session later this week. Snapshots suck.
They do suck, believe me.
So
well, most of you know.
Yeah. I knew I'd get some knowing laughs, and somehow that session name got approved. So I love this slide here, but traditional VMFS redo log snapshots have a lot of downsides, and we'll go deeper into that in that session. vSAN, starting in 6.0, implemented a completely different snapshotting system that mitigates a lot of the problems of snapshots. Combined with the other upgrades from 5.5 to 6, things like the mirror driver, getting rid of helper snaps. Again, come to that session, but virtual SAN snapshots, traditionally with a snapshot, you take it, 48 hours or 24 hours, nothing more. You want to close those things as quickly as possible. The actual steady state impact of a virtual SAN snapshot is relatively low. I've seen some independent bloggers and people say, 5 or 6% in some cases. So really opens up snapshots.
Let me add 2 more things on this. First, before I forget, not only snapshots suck, but I guess it also shows that the web client pretty much sucks because it's not capable of showing this in a decent way. The other thing that I wanted to mention.
Pandering to the cloud.
No problem. I'm quite known for bashing the web client internally, so I think it always got me fired twice so far. That's okay. The other thing that I want to mention is Christos Karmanolis actually has a session on storage futures primarily around vSAN, and he's actually going to talk about some new cool snapshot technology that we are working on. So if you haven't signed up to his session yet about storage futures, make sure to sign up for that one. Yeah, I'm going to play the music, so that I guess more or less.
We should probably head to wrapping up. So also anytime you see a session with Christos, our CTO for storage, go to those. Often, those sessions, it's small sessions, but you're sitting there with the CTO and some engineers, and they will answer some crazy questions. So One thing for resources, wanted to point out, we've launched storagehub.vmware.com. So questions not only on vSAN, but SRM and vSphere replication and virtual SAN. Our white papers are there, new content's going there. Getting an awkward look from the boss there. Also, shameless plug for the Virtually Speaking podcast. Duncan's been on several times and acted as a guest host in my absence. We discussed vSAN, we discussed storage across the industry, experts inside, people like Alan Renuth, William Lamb. Make sure to sign up for that. And then within Virtual SAN, we've got the online hands-on labs. Go check out the hands-on labs, try Virtual SAN, try the new features, evaluation. We've got vSAN assessments. Anything you wanted to leave, Duncan?
No, I just wanted to say thanks, guys, for attending. It is our pleasure to be here and to be capable of introducing vSAN and some of the cool features with that. Once again, thanks, and I hope to see you guys at one of the parties tonight, because I'm pretty sure I will be attending one. How about you, John?
I'll be out and about. So.
Cool. If there are any questions, feel free to come up. And with that, it's the end of the session. Enjoy the rest of the conference. Thanks.